Chairman, for the introduction. Thank you also to Tupac in particular for giving us this opportunity to come here and show some of our work. So I come from a different lab. There's maybe some problem with yes. Okay, so I come from a different lab, and I would say that the main interest of our lab is the development of biomedical applications based on the combination of near-infrared light, which penetrates deep into biological tissue, in association with near-infrared optical absorbers for applications in particular in the context of photothermics, where CW light undergoes thermal conversion to produce heat, and photoacoustics, where short optical pulses undergo a cascade of photothermal and thermoelastic events that produce ultrasound. And in particular, we've been focusing on the use of plasmonic particles as near-infrared optical absorbers. I will just show you a few applications that we develop in our labs today. So this is a little bit like an evergreen in our labs, which is the development of implantable devices for remote activation by the use of near-infrared light, essentially made of a biological or a hybrid component, made of hyaluronan or chitosan or other biopolymers, and containing some plasmonic particles. And we use these kind of devices for photothermal tissue bonding, for particular in the context of wound healing, or even the development of artificial scaffolds, antimicrobial hyperthermia, or controlled release of drugs that we introduce into our implantable devices, and that we activate by the photothermal conversion. But I would say that really the holy grail of this kind of applications is definitely the optical hyperthermia and photoacoustic imaging of cancer. So in this context, essentially the plasmonic particles are designed for some systemic administration, in particular an intravenous injection most often, and then the plasmonic particles should freely circulate through the body, passively, or say extravasating to the tumor microenvironment, and then in some way proactively identify the biological target, most often the malignant cells of interest, before the optical excitation for photoacoustic imaging and or the optical hyperthermia of cancer. So, as plasmonic particles, we have been focusing in particular on the use of gold nanorods, and the very striking feature of gold nanorods is their optical versatility, which is the possibility to modulate both the position as well as the composition of their plasmonic bands in terms of ratio of light scattering to optical absorbance, with their shape and their size. The preparation of gold nanorods is pretty simple and sustainable. Essentially, we typically synthesize our gold nanorods by wet chemistry, by the reduction of fluoruric acid by some mild reagent like ascorbic acid or hydroquinone, in the presence of mixtures of surfactants, very often including this tetrimonium bromide, as well as other noble metal salts most often. But I don't want really to enter too many details of the synthesis of these particles. Let me just tell you that after the synthesis, we typically modify our gold nanorods with polyethylene glycol, and polyethylene glycol provides many functions: atoxicity by the replacement of the mixture of surfactants that we use during the synthesis, that compatibility, very very high colloidal stability, as well as very high density of anchoring sites for the addition, for instance, of molecular ligands, of course, to gain molecular specificity for a molecular target of our interest, most often some malignant cells. So this is the setup that we use to quantify the efficiency of molecular recognition of our gold nanorods modified with some antibodies, for instance, and we typically measure an average of 30 antibodies and 30 events of molecular recognition per particle, even in complex biological fluids as blood serum and blood plasma. Oh yes, in the say in the standard protocol, the orientation of the antibodies is kind of random. In this paper here, for instance, we tried to properly orient the antibodies by the interposition of some microbial protein like protein A, G, L. And, but in the end, actually, we didn't find a very significant enhancement in the efficiency of molecular recognition, but a very convenient product for click chemistry just by mixing our particles with an antibody of interest of an end user. So, for instance, in this example, we targeted this cancer antigen 125, which is a transmembrane mucin that is found in many cases of ovarian cancer. And indeed, we found that our particles exhibit specificity for malignant cells that overexpress this antigen even after incubation in complex biological fluids, such as blood plasma or acidic fluids. And we actually tested many different molecular targets for many different kinds of malignant cells. We actually also tested molecular targets that do not really belong to a specific population of malignant cells per se, but emerge in the anomalous conditions of a tumor microenvironment, as is the case, for instance, for the expression of transmembrane isoforms of carbonic anhydrase in hypoxic cells, hypoxia being a very specific condition of cancer. But anytime we can observe very nice specificity for our biological target of interest. And so essentially, bottom line, our targeted gold nanorods are ready to go. So the big question here is, are we ready to go for the optical hyperthermia and photoacoustic imaging of cancer? Well, actually, whenever we inject our particles in the bloodstream, their greatest majority becomes trapped in the liver and the spleen. And the problem here is that you have to think that there actually exist a lot of biological barriers that separate the blood from the malignant cells, so that the greatest majority of our particles never even get the chance to come in contact of the malignant cells. This is a very schematic list of these biological barriers, which is the reticular endothelial system with these phagocytic cells prone to capture foreign bodies, in particular in the liver and the spleen. Extravasation out of the blood vessels. Now, you may have heard that blood vessels in tumors exhibit permeability, which is the key for this enhanced permeability and retention effect. But still, extravasation out of blood vessels is a significant barrier, and then also the interstitium in the tumor microenvironment. Okay, because a tumor is made of stroma essentially. Okay. So, in our opinion, in the end, we are probably charging our gold nanorods with too many and too high functions that are very far from their fingerprint features, which is essentially in the end just their optical absorbance. Okay, and we believe that it would be really nice to find a way to relieve our particles of some of these functions, and in particular those associated to delivery. And an interesting technology to use in association with our gold nanorods may be the use of tumor-tropic cells. Now, tumor-tropic cells is typically stem cells or cells of the immune system as tumor-associated macrophages that are actually recruited by the tumor in order to keep its microenvironment, say, as clean and orderly as possible, and so exhibit an innate ability to migrate towards the tumor microenvironment. And so the idea would be to identify a population of such cells in a patient, take them out of the patient, load them with the plasmonic particles in vitro, in the lab, under very controlled conditions, and then put them back into the host with the mission to deliver the gold nanorods to the tumor microenvironment, if you want something like a Trojan horse or kamikaze, something like this. Okay. What it takes here is just a very efficient process to couple our gold nanorods to these tumor-tropic cells without affecting their biological functions. And well, a very common strategy is the use of polycationic coatings. We have tested a few thus far, including small molecules such as these small quaternary ammonium compounds, self-penetrating peptides, and in particular arginine-rich peptides, artificial biopolymers such as polylysine. And every time we get very interesting results in terms of the amount of gold that is taken up per cell, up to something in the order of a few picograms gold per cell, retention of the particles after preparation of the Trojan horse, as well as the viability of the Trojan horse. And what we see also is that our Trojan horse tends to retain its ability to trace gradients of chemokines and migrate to an inflammatory site, as is a tumor microenvironment, as well as to release cytokines once in the presence of the tumor microenvironment, say, in order to call for more tumor-tropic cells. Okay. So in this case, for instance, we use this small quaternary ammonium compound, and we found a very fine control over the number of particles that are taken up per cell, up to something in the order of 200,000 particles per cell, which is actually really a lot. And the mechanism for the internalization is governed by endocytic pathways, and so the particles actually are confined within endosomal vesicles and do not really enter in contact with the cytoplasm, which may explain the very low interference with the biological functions of these tumor-tropic cells. And what is really interesting is that we've been able to observe our Trojan horse by the use of photoacoustic imaging in full blood down to concentrations below 1%, which is less than 1/10 of the typical size of an infiltrate of this kind of cells in the tumor microenvironment, and also to mediate a substantial photothermal damage upon excitation with CW light under min-invasive conditions. So essentially to destroy their environment, which is what we want to achieve in the tumor. So again, now the question again is, are we ready to go now with photoacoustic imaging and optical hyperthermia of cancer? Well, no, in my opinion, no. We are maybe even further than before. Essentially because this technology that we have started to use for the delivery of our particles by the use of these tumor-tropic cells is definitely immature, possibly very expensive. And on top of that, there remains rising concern on the potential of plasmonic particles to achieve regulatory clearance for this kind of applications. So at some point, say, in order to mitigate our frustration, we started to think about alternative contexts where the penetration of our particles may be smoother simply by the exploitation of their best features, which is their optical absorbance and their performance of photothermal and photoacoustic conversion. I will just show you an example which is quite interesting in my opinion, which is the design of a photothermal cycler as an alternative to, as a cheap and fast alternative actually to a thermal cycler, of course with the goal to drive a biochemical reaction through different thermal phases. Now a very interesting example is the polymerase chain reaction as a very ubiquitous tool to amplify segments of DNA in a mixture of reagents that include enzymes, primers, and nucleotides. So essentially, in the polymerase chain reaction, the thermal cycle is made of 3 thermal phases, essentially a phase of denaturation around actually 95C, where double-stranded DNA is split into 2 single-stranded halves, and then a phase of annealing around, I would say, typically 55C, where the primers bind this single-stranded DNA, okay, and then a phase around 75C, actually, I would say, where these primers grow according to the template of this single-stranded DNA, and so reproduce their other adults. So essentially, in each cycle, almost, doubles the amount of DNA that is there in the sample, and their repetition leads to an exponential amplification of the quantity of DNA that is there in the sample, and it typically takes something around 30 cycles of PCR. Now, the limiting step for the speed of the reaction is actually the design of the thermal cycler, which is a bioreactor from its outside, and this enables thermal gradients in the order of 1 Kelvin per second. So yes, and this means something like maybe 2-3 hours for a complete run of PCR made of something in the order of 30 cycles. So this is our proposal for a photothermal cycler, where essentially we propose to add plasmonic particles in the mixture of reagents in association with an LED in order to deposit it directly from the inside of our bioreactor. Then we need a probe of temperature in order to provide closed-loop control over the optical emission of the LED via something like a PID controller. And we can really simulate the entire process, for instance, by the use of console multiphysics. And the input in our simulation is the shape of the thermal cycle, the set point of the thermal cycle that we want to realize, and this governs the optical intensity of the LED, and then we simulate the photothermal conversion as the source of heat, heat transfer through models that are available in console multiphysics, and the output of the model is the distribution of temperature within the model, as well as the optical intensity that is required to achieve this temperature. So this is just an example of a result which shows the possibility to achieve thermal gradients in excess of 100 Kelvin per second, which is something about 100 times faster than the typical thermal cycler, with a power density below about 50 watts per square centimeter, a couple of watts in our design. Okay, so we enthusiastically started to manufacture our device, but we soon realized that we actually didn't quite know how to measure temperature within our bioreactor. Say deep enough, maybe about 1 millimeter, accurate enough, we need about a Kelvin to be competitive, and fast enough, higher than 100 Hertz. I mean, there's plenty of sensors of temperature around, but if you think about that, it's really difficult to find sensors that can provide this kind of performance. And so we started to think about alternative models, and we are considering a few by now, but today let me introduce the concept of photoacoustic thermometry. Now, the concept of photoacoustic thermometry is that the Grunheisen parameter, which defines the proportionality between photoacoustic pressure and product of optical absorbance and optical intensity, exhibits a striking dependence on temperature in water, about 4.4% per Kelvin, which is something like 100 times more than what happens like in typical thermistors. So in our simulations, it's essentially here we add, what we need to add here is a source of short optical pulses in association with an ultrasound transducers. And in our simulation, starting from the distribution of temperature, we simulate the thermoelastic conversion as a source of pressure in a context where pressure in the fluids is weakly coupled to temperature in the system. And then propagation of ultrasound and the structural response of the walls of the bioreactor in a context where pressure in the fluids and the stress and strain through the walls of the bioreactor are strongly coupled. So the output of the model now is the distribution of pressure in the fluids and the stress and strain through the walls of the bioreactor. So we started our simulations with a short optical pulse from an optical parametric oscillator that we typically use for this kind of applications in our labs, and so this is the typical parameters of our pulses and ultrasound transducer.
And this is the result. Essentially, we expect a level of photoacoustic pressure that is in the order of a few tenths of Pascal, right? So we know that we are able to measure this level of photoacoustic pressure, but of course here there is something that is really wrong, because I said that we wanted to develop something like a cheap alternative, a fast and cheap alternative to thermal cycler. Now I'm talking about an optical parametric oscillator, which is something that is pretty bulky and expensive, as you may know. And so we started to think about alternatives, and this is actually a very radical alternative, where we tried to completely remove any dedicated source for our photoacoustic thermometer, because essentially we are anyway driving the LED that we use for thermal cycling by the use of a PWM module, which is, the simulation of an analog output through the duty cycle of a train of digital pulses. And so we tested the efficiency of the rising edge of a digital pulse to generate a photoacoustic signal. So we started with quite conservative parameters, rise time around 50 nanoseconds. This is what 100 watts per square centimeter. This is what we need for thermal cycling anyway. But what is really interesting is that in the end we achieve a level of photoacoustic pressure which is about the same as that with the optical parametric oscillator. And so this is quite cool, because we can achieve photothermal cycling and photoacoustic thermometry with the same particles as well as the same optical source. I think I will skip this part on my slides, because I think that this was already presented by my colleague Lucia Cavigli 1 year ago. Well, let me just say that the inspiration for the assembly of my talk actually came from a visit of our friend Boris Klebsov a couple of months ago now in Florence, and of course we were like talking plasmonic particles all the time, and at some point he asked me, okay guys, after all these years of intense work on plasmonic particles, would you tell me any industrial application of these materials? At that time I didn't quite really understand the answer, which is no. There is essentially no industrial application of this kind of materials thus far. But I realized that we were maybe subconsciously working in this direction, which is the generation of contexts where the industrial penetration of plasmonic particles may be smooth and I would say at reach, maybe with the vision that strong industrial interest may one day enable the pursuit of more ambitious objectives, as are maybe photoacoustic imaging and optical hyperthermia of cancer. Well, with that, let me just, thank you all for your attention. Let me thank in particular also those who are sponsoring our joint activities, in particular this joint project between CONATIT and our National Research Council of Italy, and thank you very much for your attention again.
So, are there some questions?
Just a curiosity, how much is the temperature rise after pumping of the particles?
After for a typical photoacoustic application, extremely small. Extremely small. Well, it depends. I mean, the particles actually get very hot. The particles get very hot, and we typically tend to come very close to the level of pre-melting of the particles, which means that it's like several hundred C. But the overall temperature rise in the buffer where the particles are dispersed is actually extremely low. I would say tens of because of the tens of degree centigrade. And the photoacoustic conversion is done in the water, in the aqueous buffer, okay, because actually the breathing modes of the particles are extremely weak. So it's the transfer of heat from the particles to typically an aqueous environment, and then the thermoelastic expansion happens in the aqueous environment, where the temperature rise on average is very small. Yeah.
So a few, I don't know, 10 nanometers away from the particle? Can you estimate that?
I would say, yeah, very close to the particles, yeah, the temperature can reach very high. I would say we typically reach the critical point of water for a phase explosion, I would say. But yeah, the average heating is.
So it boils.
We can reach explosive boiling. Yeah, we can reach explosive boiling. You know, if the dynamics is really fast, you need to reach about 300 degrees centigrade for explosive boiling. Yeah.
And that's only with pulse laser excitation, or only also with continuous wave?
Okay, so it's a matter of the say thermal conductivity of water. So if you want to say localize heat within the surrounding of the particles, then you need your optical pulses to be in the nanosecond regime. I would say below the microsecond regime. When you start to exceed this regime, say I would say around 1 microsecond maybe, then essentially temperature becomes kind of homogeneous over the entire. So when you work with the CW regime, actually you should think these suspensions of plasmonic particles as like an homogeneous stain.
Other question?
You mentioned that you have obtained functionalized gold nanoparticles, and these nanoparticles are binding to antibodies. These antibodies have an oriented position, and how do you?
Yeah, actually, you know, maybe the most common protocol is to use a carboxylated polyethylene glycol or a carboxylated crosslinker, and then to activate this carboxylated crosslinker and create a succinimide ester, and then you bind. Where is that? Sorry. And then you bind your antibodies, for instance, through their N-termini. Okay, this is more or less the general principle. Now the thing is that when you do that, you can either couple your antibodies through the FC fragment, which is what you would prefer, or with the FAB fragments, which is what you would try to avoid, right? Because you want your FAB fragments to be as available as possible for the molecular recognition, right? When you do this typical protocol, yeah, in the end, the orientation of the antibodies is kind of random. Okay, so you have antibodies that are oriented like this, but you also have mis-oriented antibodies with their FAB coupled to the crosslinker, and so no more available for the molecular recognition. Okay, and there's in the literature many recipes to try to enhance the orientation of the antibodies and make sure that the antibodies are coupled to the particles through the FC fragment. We tested a very, I would say, simple solution, which is the interposition here of one of these proteins, like protein A, G, or protein L, which are proteins of bacterial origin, which tend to bind the antibodies through the FC segment. These proteins belong to a strategy of defense of these bacteria against the immune system. Okay, because you know when these microbes are bound by antibodies through the FAB segment, then they become visible to the immune system. Say, whereas if the antibody is disoriented and is bound to these microbes through the FC region, these microbes become like stealth to the immune system. Okay, so we are using these kind of proteins to bind the proteins essentially to the particles, and so we have we bind the antibodies through these proteins through their FC fragment. If you want, we can talk about that later, but the concept is actually quite simple. Yeah.
And yeah, what we found actually is that we got less antibodies per particle, just maybe because of the steric hindrance of these proteins. About the same efficiency of molecular recognition in terms of number of events of molecular recognition per particle. A slight improvement, only a slight improvement. But what is quite interesting with this kind of systems is that once you have your particles bound to these proteins, like this protein A, protein G, or protein L, then you can just mix essentially whatever antibody you want. Sorry, you can bind whatever antibody you want just by mixing your antibody with the particles. And so this is something that may be very convenient for use by something like an end user.
Final question? No? Okay. No? No? I don't know. Okay. Who wants to ask? Okay. Okay, then we thank our guests.